Taylor's formula is, I like to write out the summation, sum from k equals 0 to infinity of the kth derivative at some center divided by n factorial times x minus that center to the at k, holy smokes, k factorial to the k power. Which is looking like f of c plus f prime of c times x minus c plus f double prime of c over 2 factorial times x minus c squared, and so on and so on and so on. Every subsequent term is just the next derivative over the next factorial times x minus c to the next power. So sometimes the way you actually find the Taylor formula is by doing this process. For example, do I want to give an example? Really? But I could. This feels really kind of, there's too much light in here. It's gotten bright all of a sudden again, like the sun, holy smokes. Sure, we talked about this last time, but so for example, you could find, I'm trying to think of an example that doesn't suck. The problem is they all kind of suck. For example, you could let f of x equal, sure, x times cosine of x. So someone could say, find the first 4 terms of this. First 4 non-zero terms of f of x equal to x cosine x. Centered at, let's change it up. Centered at, no, it's not. C equals 0. One way you could do this, the long way, would be to start taking derivatives. So you could say, okay, great. F prime of x is going to be 1 times cosine of x plus x times negative sine of x. And f double prime of x is going to be negative sine of x, and then the derivative of x times negative sine of x is going to be plus a negative sine of x, and then plus an x times the derivative of negative sine of x is cosine of x. I feel like I might have picked something that's going to be 0 all the time, which is kind of stupid. Yeah, is it 0 all the time? Center not, oh, not okay, yeah, sure. Yeah, it's not 0 all the time. Yeah. And then so right, but you can see like this is going to start to get terrible. Like I can simplify this a tiny bit. I've got a negative 2 sine of x plus an x cosine of x. So if I find the third derivative, it's going to be, all right, it's going to be negative 2 cosine of x plus 1 times cosine of x plus x times negative sine of x. And we'll go one more. So that's going to equal negative cosine of x minus x sine of x. There might eventually be a pattern to this, which would be kind of cool. I'm starting to kind of see one maybe. Let's look at one more derivative. The fourth derivative is going to be, let's see, sine of x, and then product rule minus sine of x, and then and then a minus x times cosine of x. Those cancel? That's surprising. Hopefully I'm not making any dumb mistakes here. It's very possible I'm making small errors. I'm not trying to, but yeah. It's kind of cool though. Yeah. Oh, neat. That is kind of cool actually. So after 4 derivatives, we almost got back to where we started. We got to the negative. So you could probably actually continue writing it. So I will say, having noticed this, having lucked out, I can say with confidence that my next derivative, well, it should just be the negative of that derivative, right? If my fourth derivative is negative x cosine x, and the function really is x cosine x, then my fifth derivative should be negative cosine x plus x sine of x. That's kind of cool. I have not seen a lot of functions other than sine, cosine, and e to the x that have this sort of cyclical nature of derivatives. But here's an example of something slightly more complicated, x times cosine x, that after we take 8 derivatives, we would get back to where we started. Because 4 derivatives gets me to the negative of it, and if I take another 4 derivatives, we'll get back to the plus. So I know it's not like a big deal, but to me, it's kind of like I'm writing this down over here, like x cosine x. I'm gonna check this out later. Ooh, yeah, sometimes. I know. But so here, if we were going to start writing out terms, I'm going to start plugging in 0. So I can see that f of 0 is 0. F prime of 0 is cosine of 0 is 1, sine of 0 is 0, something either 1 plus 0. F double prime of 0 is looking like 0 plus 0. F triple prime of 0 is looking like -1 minus 0. It looks like every other term is going to be 1 or -1, and every other term is going to be 0. If I plug in right, the fourth derivative is going to be 0. The fifth derivative is going to be -1. Negative. Interesting. Right, -1. Yep, it's going to be -1. So I was wrong to say that it was every. But so, and look at all this work. I haven't quite gotten 4 non-zero terms, right? My fifth derivative is going to be -1. I'm pretty sure my sixth derivative is going to be 0, and my seventh derivative would finally at 0. Sorry, I'm plugging in 0, not x. My seventh derivative, much like my, not my second, but my third is going to be +1, I think. Okay, so I'm getting to the point, I promise. There is a point. It's not just for the fun of it, although you know. So if I was going to write the first 4 terms, I could do it this long way by saying, okay, so my function is going to be f of c times plus f prime of c times x minus c squared, and so on and so on and so on. So here I'm going to get, let's see, so my f of c is 0 plus, oh, sorry, not squared to the first. The next term would be f prime of c over 2 factorial times x minus c squared. So let's see, I'm going to get f of 0, and then I'm going to, yeah, it would, thank you. Then my next term would be 1 times x minus 0 to the first. My next term would be 0 over 2 factorial times x minus 0 squared. My next term would be -1 over 3 factorial times x minus 0 cubed. My next term would be 0 4 factorial times x minus 0 to the fourth. And then that, right, so we get -1 over 5 factorial times x to the fifth. The next term is 0, and the next term is +1 over 7 factorial times x to the 7. Which feels like, again, I'm always slightly worried when I do this that I've made some sort of tiny mistake, because it's easy to make mistakes. And so the thing about this is doing it this way is probably not the intention of the problem, because what you can actually do, oh no, this seems probably right, is you can say, we know that the Taylor formula for cosine x is every even power. It's going to be 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the sixth over 6 factorial. That's a plus, and so on and so on and so on. So if I then multiply that by x, okay, I'm off somehow. That's okay, we'll figure it out. So x times cosine of x is going to be, just multiply everything by x minus x cubed over 2 factorial plus x to the fifth over 4 factorial minus x to the seventh over 6 factorial. So that would be the first 4 non-zero terms of this. And now I'm sure that's right. I've obviously made some mistake doing it this way, because doing it this way is terrible. I could go back and try to figure out where my mistake is. I don't think that's a good use of our time. So while I really, really want to, I'm not going to. So, but really, I would say when you're trying to find the first so many terms of a Taylor series, often the idea is just to take something known and manipulate it. So like, for example, in this homework assignment, problem 8 is definitely like a use known Taylor series to get a thing and then manipulate that thing. Don't do the finding all the terms the long way. On the other hand, I would say problem 4 is definitely more of a do it the long way kind of problem, because it's not really that long. So that's what I say. Did you have something, Reed?
So it's asking for like the first 4 terms. What is that?
So cosine x, the Taylor series for it is an infinite series, right? This goes on forever. So plus x to the 8th over 8 factorial minus x to the 10th over 10 factorial.
So it just wants like the x.
Right. So I would write this as P4 4 of x. It's the Taylor polynomial with the first 4 terms. You might write it as P7 because usually that subscript actually refers to the degree, not the number of terms. But the idea is still the same. The first 4 terms, literally, you were stopping there, right? You're not writing out the whole thing. To that sort of end as well, sometimes we take 2 Taylor polynomials and we multiply them together. So for example, someone might ask you for the first 4 terms of f of x equal to sine of x times cosine of x. And instead of doing what we just did and taking all these derivatives and then center it at 0 and doing it wrong, the idea is to actually write out the known Taylor series expansions. So for sine of x, it's x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and write out a few terms. I usually write out 4 terms and then like that. And then for cosine of x, it's 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. And then you start kind of multiplying it out like you normally would. So if I look at this, I'm going to get x times 1, and there's no other way to get an x to the first. I'm kind of looking for the smallest powers. So I'm going to get an x. And then I ask myself, is there a way to get an x squared? Doesn't look like it. There's no way to get x times something to give me x squared. Can I get an x cubed? Yeah, and there's 2 ways to get x cubed. I can get either x times negative x squared over 2 factorial or negative x cubed over 3 factorial times 1. So I'm really going to have a minus x cubed over 2 factorial minus x cubed over 3 factorial. And I have to put that together. And then I'm not going to get an x to the 4th, but so it looks like I can only get odd powers, which makes sense because an odd function times an even function will give you an odd function. Kind of neat. So when I multiply x by x to the 4th, I get plus x to the 5th over 4 factorial. And then a minus x cubed times a minus x squared gives me a plus x to the 5th over 3 factorial times 2 factorial, which is just 6 times 2. And I'm also getting an x times x to the 4th. No, I already got that. Sorry. I'm also getting an x to the 5th times a 1. So there's 3 different ways I can get an x to the 5th here. And then you would do the same thing for x to the 7th. There'd probably be 4 different ways of getting an x to the 7th, because you'd have x times x to the 6th, or x cubed times x to the 4th, or x to the 5th times x squared, or x to the 7th times 1. So that's kind of the idea. And then someone maybe be like, what's the coefficient of your 4th term? Or let's say your 3rd term to have a 3rd term. So that if I write this out, this is x, and then here I'm going to get a plus x cubed times, let's see, 1 over 2 plus 1 over 6. Except it's negative. And then plus, I'm going to have an x to the 5th times 1 over 24 plus 1 over 12, and 5 factorial is 120. So someone could ask you to find the coefficient of x to the 5th in this expansion. And again, the idea is not to take this function and start taking a bunch of derivatives and finding the coefficient. That way it's to use known things and to multiply it out. Okay. I know I was trying not to talk too much about Taylor series stuff, but can't help it. So what I'll say about this is if we have questions about the homework on Friday, we can talk about it some more. But let's kind of go back. So what did he talk about today in class? More Taylor series stuff? Yeah. So yeah, sorry, it's hard for me not to talk about it. But let's kind of, so there's lots of other things to talk about. I know it's been a whole quarter worth of information. When I was thinking about your potential final coming up, there were 2 things that kind of I was thinking of, which was solving differential equations. And really, this was just kind of like, what do I think might be on their final? And double integrals. Now that there isn't anything else, those are just the first 2 things I thought of. What have you all thought of that might be on your final? Or have you? I mean, it's okay if you haven't. Yeah. Sure, partial derivatives. Ooh, yeah. And in that kind of vein, I would say partial derivatives, and that goes along with finding extrema, finding and classifying extrema. What about Lagrange? Do you think that? I feel like Lagrange is a maybe. Like I don't know.
Because on the last exam, he was like, what are the equations of?
Sure. Like looking at this older final. I like, at least on this final, I don't know if he's been doing this currently. Each of these questions says what it's about.
Yeah.
Oh, that's nice. That at least you kind of, I feel like that's, I mean, I like that. So let's see, looking at this final. Domain and range of a function, sure. Oh, there's a Lagrange multipliers question, so it seems reasonable. Okay. Oh, there's two. This feels like a long final. Sure. Sure. That's true. You do have 2 hours. So I'm leaving. I'm just like my kind of the older stuff. Obviously, there's also like the domain and range. To me, that's kind of all, most of those stuff. And then there's of course all the new stuff, which is, convergence, divergence, Taylor, Maclaurin, that kind of jazz. That's probably not spelled right. It's okay. Spelling, it's not a spelling class. So yeah, I guess that's kind of where I would broadly focus if I was. Yeah, we really, yes, we certainly love that. Yeah. So let's kind of cherry pick some problems for each of these things, and yeah, let's go there. So solving differential equations. There's really only 2 kinds of differential equations we can solve. It's either separable or first order. First order linear, I should say. So let's say we have the following problem. X times y prime minus 2y equal to x to the 4th times the natural log of x. And so it's your job to decide if it's first order linear or separable. Sometimes they're both. Sometimes you can do either way. To me, this problem looks like it's written in the way where we're meant to do first order linear. And if that's the case, what do we need to do to this equation so that we can do first order linear? Right. So what do I need to do to get it to the standard form? Right, because you have to have y prime by itself. And that's kind of true either way, really. Whether you want to separate or do first order linear, you kind of need y prime by itself. For separable, you need y prime all by itself, and then everything else on the other side, kind of. I mean, to start with anyway. So divide by x, and we're going to get y prime minus 2 over x times y equal to x cubed times natural log of x. Just as a point of clarification, I don't think this is separable. If you solve for y prime, so I'll just point out this is not separable. Because if we isolate y prime, then y prime would equal to 2 over x times y plus x cubed natural log of x. And there's no way of breaking that right-hand side apart into something with x's times something with y's. So definitely not separable. Okay. And also, if it's written this way, someone's clearly trying to get you to go in the first order linear direction. So now we need to find our integrating factor, which he calls mu. Okay. Then no, gamma is the other thing. That's right. Okay. Yeah. Gamma. Yeah. Okay. So mu of x is e to the integral of what? Which is what? Awesome. Good job. Sometimes people miss the negative there. So that's going to be e to the negative 2 natural log of x, which you definitely should simplify. This simplifies as e to the natural log of x to the negative 2, which is just x to the negative 2, or 1 over x squared. So definitely, if your integrating factor has a natural log in the exponent, you should make it so you can get rid of the e to the natural log and just say it's whatever's left over. But that requires bringing this coefficient up as the power there. And then he's cool with you just jumping straight to the kind of the result, right? So then our solution is always going to be y as a function of whatever variable is going to be 1 over the integrating factor times the integral of your q of x times your integrating factor dx. So in this case, that's going to be 1 over x squared. Feels silly to write, but I will write it this one time. And then we have the integral of q of x, which is x cubed natural log of x, times mu of x, which is 1 over x squared. So let's do a little bit of simplifying. Obviously, I think I should write 1 over x squared is just x squared. And then I should simplify this integrand as just the integral of x times the natural log of x. To do this integral, we do have to use integration by parts. There's no other way around it. So we're going to do integration by parts, but it's a very easy one-step integration by parts. It almost always is one step if your u is natural log. Your u is going to be the natural log of x. Your dv is going to be x dx. Your du is 1 over x dx. Your v is x squared over 2. So then this is going to become x squared times uv, so x squared over 2 times natural log of x minus the integral of v du, which is the integral of x squared over 2 times 1 over x dx. And the whole point here is, right, this new integral is easier to integrate. X squared over 2 times 1 over x is just x over 2. And the integral of x over 2 is x squared over 4. So we're going to get x squared times x squared over 2 natural log of x minus x squared over 4 plus c. And then I personally like to distribute the mu of x, or the 1 over mu of x. So I would write my answer as x to the 4th over 2 natural log of x minus x to the 4th over 4 plus cx squared. This is my general solution. And since we weren't given any sort of initial condition, we're not going to bother trying to solve for c. But I would imagine he will probably, at least in one case, give you some sort of initial condition to solve for c. That's fairly typical. Specifically for first order linear, this 1 over mu of x, your 1 over your integrating factor here, has to get multiplied by that constant. That is important. It needs to happen. Otherwise, things don't work out right. Cool. Questions about that? All right. Let's look at the other side of differential equations, meaning separable. So let's look at this one. X squared times y prime minus y squared equal to 3. And I would first observe this cannot be first order linear. It is first order, it's not linear. And what's making it not linear? The y squared. Yeah. I mean, technically you could divide everything by y, but then you have division by y somewhere, which would also make it not linear. So since it's not a first order linear, I'm going to try and make it separable. So I'm going to say, great, x squared times y prime equals 3 plus y squared. And then I'm going to try and get all the x's on the right side and all the y's on the left. So really what I should do first is rewrite this as dy dx just to make it more clear. So I've got an x squared times y times dy dx equal to 3 plus y squared. So I'm going to divide both sides by x squared. I'm also going to divide both sides by 3 plus y squared because there's no way of getting the y squared away from the 3 there. They're kind of stuck together. Addition is kind of a pain in the ass to undo when you're talking about separable. So I'm just going to put some parentheses around this to remind myself that they go together. And then I'm going to say, okay. I'm going to say, okay. On the left-hand side, I want y times dy. And I also want to divide by that 3 plus y squared. On the right-hand side, I want the dx to come up and to divide by x squared. Yeah, and then we're going to integrate both sides. And I rewrote x, 1 over x squared is x to the next second. Y over 3 plus y squared is a pretty straightforward u substitution. We can let u equal the bottom, and du is essentially the top, except we're off by a factor of 2. So u is 3 plus y squared. Du is 2y dy. So 1/2 du is equal to y dy. So there's my 1/2 du. There's my u on the bottom. So this left-hand side becomes the integral of 1/2 du over u. The right-hand side, I know how to anti-differentiate x to the negative 2. It's x to the negative 1 over negative 1. Integrate the other side. We're going to get 1/2 natural log of the absolute value of u. I would totally rewrite x to the -1 over -1 as a negative overall in front, and instead of x to the -1, a 1 over x. And then well, not finally. And then I would say 1/2 natural log of 3 plus y squared. And I'm going to drop the opposite value because normally I would anyway, but specifically here because 3 plus y squared is always positive. So I really don't need it. And I guess we're probably expected to solve for y. It's kind of a bummer, but oh well. So multiply both sides by 2. The natural log of 3 plus y squared equals -2 over x plus a new constant. I'm going to call the same constant. And then e both sides, so 3 plus y squared equals e to the -2 over x plus c, which we of course rewrite as e to the -2 over x times e to the c, or e to the -2 over x times, what do you like to use? A, me too. And then I would subtract 3 from both sides, so y squared equals a e to the -2 over x minus 3. And finally, ooh, yeah, I'm going to throw in, so if I was doing general solution, I would say y equals plus or minus the square root of a e to the -2 over x minus 3. Well, let's go ahead and throw in an initial condition here. So even though there isn't one in this problem, because I think this is where things get interesting. So let's say our general solution was this, that y equals plus or minus. Ooh, that's going to be interesting. I need to be careful here. Yeah. Okay. So here's why I need to be careful. I was about to say, let's say that our initial condition is y equal to something when x equals 0. X equaling 0 would be a big problem because we have a division by x. So I'm going to make up something that's probably going to come out to be terrible. But let's say our initial condition is that y of 1 is equal to -4. Now, here's what I want you to see about this, because I think it's interesting, one, but also could actually come up. Someone could ask you to think about this. So once you're given an initial condition, you actually get to say which piece of the square root we actually want. Do I want the positive part or do I want the negative part? Well, for y to be negative, it has to be the negative part. There is no other option. So we know that our actual solution is going to be y equal to negative square root of a e to the -2 over x minus 3. And then to solve for a, we're going to plug in -4 for y and +1 for x. And then this just becomes a process of solving for a. So we multiply both sides by -1. I guess you could just square both sides, but I feel like it's better to say first I'm doing this. Then we square both sides, so 16 equals a e to the -2 minus 3. Add 3. Divide by e to the -2. Or specifically, a equals 19 e squared. And I would be remiss if I didn't mention that this is not where you stop. You have to plug it back in to actually write your final particular solution. So our particular solution would be y equal to just negative, not plus or minus, the square root of a, which is 19e squared times e to the -2 over x minus 3. And if you were someone else, you might combine those e's together and write it as e to the 2 minus 2 over x. That would also be totally fine. And then you can plug in 1 and see that you get 4 if you really wanted to. And you do, right? Because you plug in 1, 2 minus 2 is 0, e to the 0 is 1, 19 times 1 is 19, minus 3 is 16, and the square root of 16 is 4. Totally works. Cool. All right, let's do something else. Again, if you guys have questions or specifically want to see a thing, let me know. I was going to do some sort of optimization problem, or would you or a double integral? What do you think? Do a double integral. I like double integrals. Sure. So let's look at this one first. And so I would say if I were doing a double integral problem, or if I were giving my students a double integral problem, I would definitely give them at least one where they had to change the order of integration. That's kind of one of the most important things about learning how to do double integrals, at least in this class. Again, all this with a grain of salt, because important how, I don't know what you're going to use this for later on. Maybe you'll never use double integrals again. You're certainly not using it in your next math class because you're not taking a next math class. So sure, but definitely stats. I don't count it as a calculus class. It's certainly a math class, but you don't need to use any calculus in it. So
are any of those even more math? I raised my hand like stats, and he was like, stats isn't technically math.
right. You use math and stats, but it's really more about interpreting the information into meaningfulness. So if I look at this here, the integral, so again, pretending like 4y is a constant for a second, because we're looking at integrating with respect to x first. The integral of 1 over x squared plus 1 squared, although technically possible, is really, really hard to do. And requires a method that we haven't learned in this class, and we won't learn in this class. It requires a method called trig substitution, which we don't learn in 16C. But obviously, or at least I think obviously, if you see this and you're like, that looks really hard to do, the thought process should be, that means I probably should switch the order of integration. So I should draw the region of integration. Draw the region. We know our curves are going to be where x is going from y squared to x equals 4, and then y is going to go from 0 to 2. But you always want to draw the inner region first. So x equals y squared is a rightward opening parabola. And x equals 4 is a vertical line. But then y is only going from 0 to 2. So we're only getting the top half of this region. So there's my region. And now, instead of using what I would call horizontal strips to describe it, right, where we're bounded on the left by x equals y squared and on the right by x equals 4, and then we go as low as 0 and as high as 2. Now we're going to use vertical strips to describe it. So the bottom boundary for this vertical strip is, of course, y equal to what? And the top boundary is y equal to, right, because it's x equals y squared. And it's specifically, now I think a more interesting question would have, I'll get there in a minute. We'll do this and I'll talk about a more interesting question. Yeah, well, that's a smart, I could see, yeah. Sorry, I got distracted. Y equals square root of x. And then our x bounds are going to be as far left as 0, as far right as 4. So we're going to rewrite this as the integral from x equals 0 to x equals 4, y equals 0 to y equals the square root of x of 4y over x squared plus 1 squared dy dx. I do think it's totally fine to write y equals or x equals on the limits of integration if that helps you. It definitely helps me. That's why I write it. And there shouldn't be any reason why you can't write it. And now integrating this is really straightforward. If you like, and I kind of do like, I might rewrite it so that I can think of the y part separately from the x part. So I might write this as 1 over x squared plus 1 squared. That's just my constant for now, times my 4y. I guess the 4 I could have brought over there too, but whatever. So then when I anti-differentiate 4y, I get 4y squared over 2, or 2y squared. So I'm going to get 1 over x squared plus 1 squared times 2y squared. Right, because I'm just anti-differentiating this from y equals 0 to y equals root x. So then I plug in root x for y, and I get the integral from 0 to 4 of 1 over x squared plus 1 squared times, let's see, 2 times the square root of x squared is just x. Minus, so if I plug in 0, I get 0, so I'm not going to write that down. And then I think we can see the u substitution that's going to happen, which is pretty typical when you do this change of order things. That it becomes easier because the hard part then becomes a nice u sub. So then we would let u equal x squared plus 1. Our du is exactly 2x dx. So there's our du. There's our u. And so we're going to rewrite this as the integral of 1 over u squared du. And I personally would change my limits of integration here. If x is 0, u is going to be 0 plus 1. If x is 4, u is going to be 16 plus 1. If it's easy to change limits of integration, I think it's worth doing just because then you don't have to like write the changing back part at the end. So I would do that. And then we're going to integrate 1 over u squared, which is u to the negative 2, and get u to the negative 1 over negative 1 from 1 to 17, or negative 1 over u from 1 to 17, which is negative 1/17 minus negative 1 over 1, or 1 minus 1 over 17. Or 16 over 17. It's kind of a nice answer for a problem that looked like it could have been terrible. So the thing I was thinking to myself that I thought might be interesting to ask here is instead, if the double integral had, instead of being from 0 to 2 here, it had been from negative 2 to 0. So I could see asking a question like this on your exam. So instead of giving you the double integral and expecting you just to know you should change limits of integration, writing something like rewrite the double integral from negative 2 to 0 from y squared to 4 of 4y over x squared plus 1 squared dx dy as a, in the opposite order. I don't know how you'd phrase it in the opposite order. And I could totally see asking a question like this and saying to not integrate it. So that kind of goes back to a bigger thing, is that make sure you read the questions carefully, right? Don't do more work than you have to do. There might be a problem where it's just like set up the integral or find this thing, but don't do this other thing. So always be aware of what you're being asked to do. So if we were doing this, I would do the same sort of thing as the previous one. I would draw the region. There's my x equals y squared again. Here's my x equals 4. And my picture doesn't have to be perfect. I'm just trying to get an idea. But then y is going from negative 2, which is right here. That's the point. X equals 4, y equals negative 2, to 0. So I'm really just getting this region here. So I was going to rewrite the integral now using vertical strips instead of horizontal strips. My inner limits of integration are, well, what's my bottom boundary here? Right, because when you solve for y in terms of x here, you're getting actually y equal to plus or minus the square root of x. And the top part here is y equal to the positive square root of x, because y should be positive. And the bottom part here is y equal to the negative square root of x, because y should be negative. So if I was rewriting this region, it would be negative root x to 0, and then x would still be going from 0 to 4. And then still be the same integrand, 4y over x squared plus 1 squared, and then it'd be dy dx. So I can see that being a slightly trickier version of this question, to see that you have to have the negative root x there instead of the positive one. Again, I know we're not usually trying to be extra tricky, but sometimes people like to throw in a little twist just to make sure you're kind of paying attention, I guess, is how I could justify that to myself. Sure, let's look at one more double integral and then, yeah, okay. So here's a double integral that requires no integration. So if someone just said, find this using whatever method you want, you could certainly, well, maybe, no, maybe not. I don't know if we actually can do the integral here. So let's say we did the first step and we got the integral from 0 to 2 of the integral of 1. I like to throw in a 1 there. It's just going to be y from 0 to the square root of 4 minus x squared. Which then I would write as the integral from 0 to 2 of the square root of 4 minus x squared. But I don't think we know how to integrate the square root of 4 minus x squared. In fact, I'm sure of it. And the idea is that we don't have to, because if we know what this looks like, we can use some area formulas. So if you remember, y equal to the square root of 4 minus x squared is the top half of a circle of radius 2. If it helps, and I think it does help, you can square both sides and then bring x squared to the left. And then it's a little easier to see, oh yeah, that's a circle. So that's the top half because y is positive there. So we look at that. Now here again, we still have to be careful because if we say this, you might say, oh, it's going to be 1/2 times pi times 2 squared. But it's not 1/2, it's 1/4 because x is going from 0 to 2. So we're really only getting 1/4 of the circle. So this is going to end up equaling 1/4 pi times the radius squared, which is just pi. So sometimes with double intervals, people like to be tricky. Sometimes not. I don't know. I'm trying to think of all the various. I mean, I feel like he could ask you really lots of different things, and I don't think he's going to try and trick you. He's going to try and ask straightforward just questions that just make you think about what you have to do. Let's look at some classifying extreme problems. Let's see. Sure, here's a good one. Let's say we've got f of xy equal to 4x squared y minus 8x squared minus y squared. I want to find and classify the relative extremes. So of course, we take the partial derivatives from equal to 0. So fx is going to be, let's see, 8xy minus 16x equal to 0. Fy is going to be 4x squared minus 2y equal to 0. And if it's up to me, I'm always going to pick the one where I feel like I can actually get some numbers out of it. So if I look at the second equation, I can't really get x or y equal to any particular number. I mean, there's lots of answers, right? X and y could both be 0, or x could be 1 and y could be 2, or x could be 2 and y could be 8, and so on and so on. This is right, because really if I solve for y here, I'm going to get y equal to 2x squared. And so there's a whole parabola's worth of possible solutions. So instead of focusing on that, let's look at this first one where I can just do some factoring. I can factor out an 8x, I'm left with a y minus 2. If I set that equal to 0, I get two possible solutions. I either get x equal to 0, y equal to 2. Now let me ask you both. Is 0, 2 a critical point? Good. Good. So I want to make sure. So then we take that and we go to the other equation. So if x equals 0, we're going to get negative 2y equal to 0. So we're going to get y equal to 0. So 0, 0 is a critical point. Similarly, by plugging in y equal to 2, you're going to get 4x squared minus 4 equal to 0. So x squared is going to equal 1. So x is going to be plus or minus 1. So we're going to get either 1, 2 or negative 1, 2. Word of warning, sometimes you end up getting a no solution from one of these equations. Like for example, just in pretend world, if y equal to negative, 8 had been a other value we got from this first equation, then we plugged it back in over here, you would have 4x squared minus 2 times minus 8 is plus 16 equal to 0, and that would have no solutions because you have x squared plus a number trying to be 0, and it can't be. So just be aware, occasionally one or more of these values you get from one equation plugged into the other equation actually doesn't yield anything. You still should always get some critical point. You just might not get as many as you think you're going to get. So then we're going to test these. We're going to find gamma, my favorite. fxx is going to be 8y minus 16. fyy is going to be negative 2. And fxy is going to be 8x. Yeah, 8x. Yep, that checks out. And fyx is also 8x. I do like to check the other one just to make sure that they're the same. If they're not the same, I should definitely go back and recheck my work because something's going on there. They should be the same. So then gamma is going to be 8y minus 16 times negative 2 minus 8x quantity squared. And then if I plug in 0, 0, I get negative 16 times negative 2, so 32 minus 0, which is positive. So do I have a saddle or do I have a max or a min? Max or a min. Now, knowing that both fxx and fyy, well, knowing that just looking at this, fyy is always negative. So I know it's a max, right? Yeah, because it's concave down. I have to be like, oh yeah, concave down, max, great. Max. Because fyy is negative. My gut bet would be that the other one's going to be a saddle. Like if I were asking a question like this, I would try and come up with a function. If I had there's 3 critical points. I would try and come up with a function where I had at least one saddle and at least one max or min. So my guess is going to be a saddle. Let's check. So gamma of 1, 2, if I plug in 1 for x and 2 for y, I get a negative number because 2 for y is going to be 0 there minus 8 squared. So saddle. And the same should be true for negative 1, 2 as well. So gamma of negative 1, 2 is also 0 times, well, it's going to be times negative 8 squared. It's still negative. So also a saddle. Cool.